So for here, we're going to start with a known series. Okay, so we're going to start with that known series cosine x, and then we're going to generate a new series x cosine x. And then using that new series, the sigma notation for that new series, we're going to check for the radius of convergence. So the known cosine's known series, because we worked it out the last time, it's also one, it's a fairly standard series. So to generate this x cos x, we're just going to take x and multiply it by this series for cos x. So here's the series for cos x. So to generate the function x cos x, we just take, so we have x cos x. That's just going to be equal to x times that series. So we end up from -1 x to the 2n all over 2n factorial. Okay, so algebra of these series, well, this is multiplying every single term of this series. So then I can work out this series by algebraically manipulating this. And my new series for the x cos x function is going to look like this. It's going to be -1 to the power n. X is going to go inside there, so this becomes 2n plus that extra x from the outside. And this is all over 2n factorial. Okay, so now we have our series form of our sigma notation form of this series. So this is a series that will generate a graph for x cos x. Okay, so that's one part. We can just make new series in this way. But we also want to know if what the radius of convergence is. So we're going to do practice doing our ratio test. So the limit as x goes to infinity. Okay, we're going to take that -1 n plus 1. This is going to be x to the 2n plus 2 divided by 2n plus 2 factorial. Okay, remember I'm putting the n plus 1 into the n, so I need to multiply that plus 1 by 2 as well. Okay, just going to move this down a little bit so it's not so crowded. Okay, and then I'm going to divide that by the previous term, the original term here, so I'm going to end up with -1 to the power n, x to the 2n plus 1. Sorry, this is going to be 2n plus 3, isn't it? Because we have 2n, when we substitute the n plus 1 into here, we're going to get into a 2n plus 2 plus 1, so that's going to be plus 3. So that's going to be plus 1 here. And so on the denominator, we just get 2n factorial, and we want to know where this ratio is less than 1. Okay, so then we just need to simplify this. We need to group our parts together. So I'm going to group my -1. So I get -1 to the n plus 1 divided by -1 to the n, which leaves me with 1 -1. 2n plus 3 divided by 2n plus 1, we're just left with x squared. And then the factorial parts, we're going to end up with 2n factorial on the top. Okay, and then we're going to end up with 2n plus 2 factorial on the bottom. Now to simplify the factorial parts, we just have to make sure we understand the number of factors involved. There's 2 extra factors here. So I'm going to write it like this. N goes to infinity, -x squared. And this 2n factorial, I'll leave like that. The 2n plus 2 factorial I'm going to rewrite as 2n factorial, which allows those to cancel out. Then I have the two extra terms of 2n plus 1 times 2n plus 2. Okay, so that's equivalent to 2n plus 2 factorial. Now I can cancel out some terms. I can cancel out some of those factorial terms. I'm just left with that fraction here now. So I can then apply the limit. Okay, so I'm going to, well, simplify first and then I'll apply the limit. Limit as n goes to infinity, negative x squared. This is going to be 1 over 2n plus 1, 2n plus 2. Okay, and then we're going to now apply the limit. Let n go to infinity. That's going to end up going to divide by infinity, which is 0. So x squared times 0 is less than 1. Well, anything times 0 is 0. So anything I multiply with anything I substitute for x, I'm going to end up with 0, which is less than 1. So x in this case ends up being all real numbers. Okay, so the radius in this case is infinite. So my radius of convergence, okay, this is infinite. I have an infinite radius of convergence. Okay, and so the domain of this function is XER.